to try a couple more of these synthesis problems and give you some ideas on how to do them. These are the medium-ish retrosynthesis problems. You know, I don't know, they're sort of ranked by difficulty, but some of them are actually kind of easy still. Alright, so this one will be apparently a conversion of a bromide to this sort of alcohol with a phenyl group on it. And like before, I'm going to do these on my own sheet of paper. So obviously the part that's being attached is the phenyl. So let's see if we can do this one. This is problem F. Okay. Alright, so let's look. We have a bromide on a tertiary carbon, and we're doing a synthesis, and we're making, looks like a hydroxy group there, and a phenyl, which is just a benzene, right? And so we're attaching the phenyl, and there's the squiggly line. Obviously that's being attached, so it's probably going to be a Grignard type thing. And it'll be interesting how we navigate our way back to the bromide, because we're going to go backwards, right? But given just the CC bond forming part, because we're making this carbon-carbon bond, we can just focus on that. We're going backwards. Let's see what happens. And since the squiggly is next door to the OH, that would suggest what kind of intermediate in this as a Grignard style reaction. What kind of thing? I mean, like, would the, because that part will be the electrophile, would that be a formaldehyde, aldehyde, ketone, or epoxide? And the answer is, well, the squiggly is next door to where the oxygen is, so it would be an epoxide. So what would that epoxide look like? It would just be essentially that, but as an epoxide form, which would mean you'd have an epoxide between the carbon, the oxygen, and that carbon. So let's see how that would look. There you go. There's our nice epoxide. And what would we add as a Grignard? Well, it would be that. But as a Grignard, it's a benzene, phenyl Grignard. So phenyl and GBr. H2O. Alright. Cool. That would be the nice last step of this synthesis. Alright. Alright, so then how do we work our way back to the bromide? Well, I mean, this is pretty straightforward. We know how to make epoxides. How do you make an epoxide? So you make an epoxide from what functional group? The only way you really know how to do it is from the alkene. So let's go back to the alkene. And then we'll eventually work our way backward to that bromide. So what's the reaction, the reagent to convert an alkene to an epoxide? This is chapter 12 stuff, but we learned it in chapter 9 even. 5 letters, MCPBA. MCPBA is the really cool way to go from an alkene to an epoxide. Okay, so then, not quite done, but we're close. Now we're going from a bromide to an alkene, and now whenever you go from a bromide to an alkene, or a leaving group to an alkene, you have the question of, do you want to do it Zaitsev or anti-Zaitsev? Zaitsev would make a more substituted alkene, like this alkene. I'll show the anti-Zaitsev too, just for fun. But this is definitely Zaitsev, all right? Zaitsev. And to do Zaitsev, you'd use a base. You use a base, and you would use a kind of non-hindered base, so like NaOCH3. Of course, we don't need mechanisms, but what is the mechanism? It would be, it's such a simple mechanism that I can kind of sneak it in there, even though we don't usually do mechanisms on synthesis problems. but the base takes the proton, makes the alkene like that, right? So that would be a Zaitsev formation of an alkene. What chapter is that? That's chapter 11? 11, yeah. The end of chapter 11 is that. But how would it look if it was anti-Zaitsev? It would be, and what reagent would you use for anti-Zaitsev? You'd use a hindered base. I'll draw it down here. For if you want to do an anti-Zaitsev elimination reaction, you would use, and we have a Br there. You'd use a hindered base like Na or KOTBU, tributyl, right? A nice big hindered base like that, and then that would actually go after the sterically available proton to kick off the Br, and then the Br would pop off there. So it was drawn a little poorly, but yeah, base takes proton from the more accessible position, which is that CH up there, kicks off the Br, and then you get an alkene that looks like this. Okay, that would be the anti-Zaitsev, but that's not what we wanted here. So, okay, cool. All right, that's problem F. I'll erase this one. All right, next problem. Alright, so it looks like we're going to do problem G now, which is like this alcohol with 4 carbons, 1, 2, 3, 4, with an alkene on it, and then how many carbons do we end up with? 1, 2, 3, 4, 5, 6. So it's going from 4 carbons to 6 carbons. Hint says count your carbons, how many are being added, and then we might need protection. That's probably going to be the case. We might need protection. And why do I say that? Well, I mean, if I just count these 4 carbons, 1, 2, 3, 4, and I say, well, those are probably these carbons, 1, 2, 3, 4, that means we're adding 2 carbons. Looks like we're adding 2 carbons. And if we ignore this hydroxy for now, this alcohol, that's actually you know, and just looking at the squiggly and where the OH is, it would kind of suggest that this carbon would be made into a Grignard, and then this would be a, what are our 4 types of electrophiles? Especially, okay, so formaldehyde, aldehyde, ketone, and epoxide. Of those, since the squiggly is 1 carbon away from the OH, it'd probably be an epoxide. So it'd be maybe a 2 carbon epoxide, right? A simple 2 carbon epoxide would be the way to build this. But then we also have this other alcohol. And all we got to do is really protect this one, which will be, we'll protect it with our protecting group, and then we'll carry the synthesis forward and then eventually unprotect it. So let's see if we can do it. Problem G. Okay, so we got our, what's it, 1, 2, 3, 4 carbon piece, and we want to make a 6 carbon piece. So reorganize a bit here. Alright, 6 carbon piece. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It looks like we're making a bond between 4 and 5. There's a squiggly. You know, and given that it's probably going to be a protection of this and a deprotection of that, sometimes what I do is I start with the protection step. So the protection step is making a tert-butyl ether. You do that with tert-butyl alcohol and acid, and so that would make oxygen, tert-butyl. Dun, dun, dun. Now we have a protected alcohol over on the left, and we have the alkene here. And then we're going to keep going. At the very end will be a deprotection of that one. So that would be oxygen. 1, 2, 3, 4, 5, 6. Okay, cool. So now we still got to work our way backward, but also yeah, that's the protection reagent. How's it work mechanistically? We don't need the mechanism, but if you were doing a mechanism, basically that oxygen would grab the proton, become a good leaving group, fall off, then you get a carbocation, and then this alcohol would attack the carbocation, right? Okay, to go the opposite way, you just use a non-nucleophilic acid like H2SO4 or H3O+, and that is almost the opposite, where the oxygen would get the proton, protonate it, fall off to make a tertiary carbocation, and then water or something would take off the proton. Your byproduct is always this alkene, so you can try that mechanism. It's an E1 reaction. E1. E1. Of course, this was an SN1. But we really don't care about mechanisms right now. We're just trying to get our synthesis working. Okay, but that solves the issue of the alcohol. Let's do our numbering again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we're going to make a bond between what and what? 4 and 5. So now we somehow just have to form a bond between carbon 4 and carbon 5 using our standard method of Grignard. And we said already it's going to be a 2 carbon epoxide, so 5 and 6 will just be a 2 carbon epoxide. 4 will be the Grignard. 4 will be the Grignard. So to do that, all I do is draw an arrow. I redraw the left part as a Grignard. So carbons 1 through 4 with the Grignard. One, two, three, 4. 1, 2, 3, 4 MGBR. And then 5 and 6 will be the what? 5 and 6 will be the 2 carbon epoxide, and that's because the squiggly is 1 carbon away from the OH, so H2O. And that would be 5 and 6. And mechanistically, of course, carbon 4, I can make a dot, attacks carbon 5, I can make it a dot, and that makes carbon 4 and carbon 5. Okay, good. Let's see how we can keep it going backwards. How do you make a Grignard? How do you make a Grignard? You do it from the bromide. One, 2, 3, 4 Br. Cool. What's the reagent? Mg. Cool. So now all we got to do, I mean, we're very close now. All we have to do is convert an alkene to a bromide. And alkene to bromide. So you think of your reactions in chapter 12 that convert an alkene to a bromide. Is this a Markovnikov bromide or an anti-Markovnikov bromide? It looks like if the bromide's going on in the end, it's not a Markovnikov bromide, but it's an anti-Markovnikov bromide. And you are adding HBr. But it's not just HBr. To make it anti-Markovnikov, it's HBr plus something. Peroxides. If you want to draw the peroxide out, it's terbutyl, oxygen, oxygen, terbutyl. Diterbutyl peroxide. And we solved it. Now we've solved the synthesis. That was pretty fun. Problem G was a little treacherous, maybe more treacherous than the other ones. Let's try problem H. H is actually pretty easy. Maybe, I don't know. Yeah. It's relatively easy. H looks like you're going from a cyclic alcohol to apparently a molecule that's cleaved. So the ring is gone. And of course, the hint is, how many ways do you know to cleave CC bonds? And there's really like one, which is ozenolysis, right? Ozenolysis cleaves alkenes, and it gives you things that look like, you know, aldehydes and ketones, and here is 2 aldehydes. So let's see how we can maybe approach problem H. Okay, so problem H, oops, is cyclohexanol. And we go on to aldehyde, aldehyde. 1, 2, 3, 4, 5, 6. So 6 carbons in, 6 carbons out, right? 1, 2, 3, 4, 5, 6. Okay. So all we got to do is, again, work backwards, and we only know one way to cleave bonds. So maybe we can just envision cleaving a bond, maybe a ring that contains how many carbons? 1, 2, 3, 4, 5, 6. Ah, kind of like that. But you need an alkene, so let's make an alkene. Maybe we can call it that. Cyclohexene. And what are the reagents to cleave a alkene to give you like a pair of aldehydes or ketones or whatever? In this case, the alkene gets cleaved, and so that alkene gets cleaved, and you get an aldehyde and an aldehyde. So what are the reagents? It's it's O something. It's actually O3, ozenolysis, and it's O3 and then zinc and then acetic acid. So you can look that up on your little chart of chapter 12 reactions. Okay, so now it's just a matter of how do you go from an alcohol to an alkene. That can be done in one step. Do you use acid, but do you use a nucleophilic acid, which would give you probably a carbocation and like a bromide, or do you just go directly to the alkene? And the answer is, if you want to go from the alcohol directly to an alkene, you can use a non-nucleophilic acid, like H2SO4. And that will protonate the oxygen, and then the oxygen falls off, carbocation, and then water takes off the neighboring proton, and you get the alkene. So H is actually a pretty easy problem. Now let's try I. So I looks kind of similar. We're starting from a 6-member ring with the bromine. But, so six carbons in. Let's see how many carbons we got out. 1, 2, 3, 4, 5, 6, 7, 8. Looks like we have 8 carbons out. So we must be adding carbons, right? Somehow. Okay, and it says count your carbons. Simple extension of the previous problem. So it's actually going to be very similar to the previous problem, where, you know, say we cleave a 6-member ring, and say we'd somehow make this aldehyde. Say we go somehow from here to there. This can be converted to this really easily. How? So the answer to H can be converted to the answer of I very easily. How would you do it? Let's look at that. I mean, what are we adding? We're adding it looks like we're adding a carbon at the end on the left end, and we're adding a carbon on the right end. So it's just a CH3 and a CH3. How can you do that to an aldehyde? Oh, that's really easy. It's draw it. It's like CH3 MGBR, right? Methyl Grignard. Right, that would add a methyl to both aldehydes. A methyl to that one to make a secondary alcohol, methyl to that one to make a secondary alcohol, and there's your 2 secondary alcohols, right? And then water. So how do we put that all together? Now we just have to start from a bromide instead of an alcohol. But the bromide can be converted to an alkene the same way. This was made into an alkene with acid. This is made to an alkene with base. So E2 reaction, right? So let's try it out. I. So problem I now. I can do this pretty quickly because we just explained how to do it. So for I, it's a bromide. Arrow, arrow. To the alcohol. Cool. So we make these two, we attach those two CH3s from the dialdehyde with CH3, MgBr, water, and you can do that from the dialdehyde. So therefore we have 6 carbons here, just like we had 6 carbons there. We're adding 2 carbons, 1 to each aldehyde, and that gives you the alcohols. I'll even draw a CH3 at the end if you want. Cool. Okay, so then we do make this also from what the aldehyde, dialdehyde you make from the alkene, just like we did before. How do you do that? You cleave the alkene with what? O something. It's a O3. O3 zinc acid. And then to go from the bromide to the alkene, you use a base. What base? Your choice. We could say NaOCH3. You could also do like even a NaO terbutyl. There's no Zaitsev or anti-Zaitsev issues here. So it's just any strong base of your choice. NaOCH3 or NaO terbutyl are the bases we usually use. Okay, let's try the next one. I think it's problem J. It looks really scary. Maybe the product might look scary to you. I mean, it's simple ketone and got a couple things going on. It looks like we're adding a methyl. So we're adding a methyl somehow. That's somehow being added, right? We're also adding this weird cyclopropane thing, right? Dichlorocyclopropane. That was actually given to you. We saw how to do that. That's a chapter 12 reaction, and if we go back to our little chart, we'll see that we did learn that actually. It was the we saw it right here. It was the from a methyl cyclohexene CHCl3. It's called chloroform, CHCl3, and a base, super strong base. It was that carbene thing we talked about. Anyway, it just magically snaps on the carbon and the 2 chlorines, and you make a 3-member ring, just like we want. So let's use this reaction we learned in the context of this synthesis problem. So that's problem J. Okay, let's try it out. So I'm going to redraw it on my paper. Okay, we're on to problem J, which is ketone. Got some steps, and then we are making, apparently it looks like a methyl and a cyclopropyl with the 2 chlorines on it, like that. Okay, so probably we can just attach this. I'm going to make a squiggly through the cyclopropane, like squiggly, because we're attaching that piece, right? That's being attached. We know how to do it from the alkene. So assuming we have the alkene, we can do it. So how do we do it? We draw the alkene. There's the alkene and the methyl. And then what's the reagent? It was HCCl3 H or CHCl3. The drawing as is possible too. It's just an H and a C and 3 Cls. Chloroform. And then it's a strong base like KO butyl. Nice strong base. That is the way to turn an alkene into a dichlorocyclopropane. Now, how do we go from this ketone to this guy? We obviously have to attach the methyl too. So somehow we got to attach the methyl, but we don't know how to make it. We don't know how to attach a methyl in a way that gives a alkene like that, right? We don't. When we attach a methyl or we attach something, it always makes an alcohol, right? Through a Grignard attack, formaldehyde, aldehyde, ketone, epoxide, etc. And so anyway, let's envision making this from the alcohol, because we know how to make alkenes from alcohols. So if we have a methyl and an alcohol, we know how to do that. We know how to go from an alcohol to an alkene. We dehydrate, right? It's an E1 reaction with what? A nucleophilic acid or non-nucleophilic? If there's a nucleophilic, it would turn the OH into a Br. If it is non-nucleophilic, it converts the OH into an alkene. And that's what we want. So we use a non-nucleophilic acid like H2SO4. Cool. And now this is actually simple. We go from a ketone to a molecule with an alcohol in the methyl group. How do we do it? Just simplest chapter 8 stuff in the world. We just draw the little squiggly right there. Of course, it's a methyl addition to which functional group to give a tertiary alcohol? Is it attacking a formaldehyde, an aldehyde, a ketone, or an epoxide? Well, the methyl is right next to the oxygen, so it's a ketone, and we're actually given a ketone, so that's all set up, and all we have to do is a 1,2, water, and what nucleophilic reagent would attach that methyl? I'll draw it over here, CH3 MgBr, right? Methyl would attack the ketone and give the alcohol. So that was fun. We did it. Okay, we're on to problem K, which is actually incredibly easy. I don't know why this is on the medium-ish synthesis problem list. It's really not that difficult at all. We're taking an alcohol and we're attaching an isopropyl. But remember, you can't do that directly. It's not a one-step process. So let's try it out, and this helps review some of the reactions that you might have forgotten. This is problem K. Alcohol. And alcohol with isopropyl. Okay, so we can immediately just attach the isopropyl from a Grignard reaction. What's the nucleophile? That isopropyl Grignard. What's the electrophile? Squiggly is next to the OH. So it's tertiary alcohol. So it's formaldehyde, aldehyde, ketone, or epoxide. It looks like ketone, cyclohexanone, right? So it's just the ketone. What's the reactive nucleophile? Grignard, isopropyl Grignard. Doesn't have to matter how I draw it. It's all the same, H2O. So now it's just a matter of how do we go from an alcohol to a ketone, and this is where students forget this stuff, so it's good to review. First question might be, is it an oxidation or a reduction? I mean, we're going from 1 bond to oxygen to 2 bonds to oxygen. That's an oxidation. Often students say, oh, it's NABH4, but that's not true. NABH4 is a reducing agent. NABH4 goes the other way. So if I had a alcohol and I want to make ketone and I want to make an alcohol, you use NABH4. Whoops, sorry, I didn't draw it. Yeah. If you have a ketone and you want to make an alcohol, NABH4, the mechanism is H minus attacks, and you make an alkoxide, and then gets the proton, and then you make the alcohol. But that's not what we're doing. We're going the other way, which is from a alcohol to a ketone, so it's an oxidation, and you use PCC. PCC is a chromium reagent. That's a good oxidizing agent. Oxidizing agent. If you want to review the structure of PCC, which you don't need to memorize, it's chromium, double bond O, O minus, Cl. That's PCC. There's a counter ion. It's pyridinium, which I'll draw just for reference. It's nitrogen. It's a benzene with a nitrogen in it, and an H and a plus charge. So that's not drawn too well. It's basically, I'll draw it better. Try again. Nitrogen. There we go. So it's this complex, which is pyridinium chlorochromate. It's chlorochromate. It's an oxidizing agent. Very nice way to go from a secondary alcohol to a ketone. Alright, so it's K. Very easy problem. All we did was we oxidized and then we did a Grignard. Problem L is a little more challenging. It's going from a ketone to this thing with more carbons and also a ether. So it's actually maybe one of the most challenging problems, but it's still within our grasp and it's doable. Let's see how we do this. Problem L. So I'll draw it out on my paper. Redraw it on my paper. L. Benzene. Ketone. Arrow, arrow. Five-member ring. O, CH3. So all we got to do is systematically kind of go backwards and kind of do it in the right order, obviously. We might think about some attachments. What is being attached? Well, it looks like this is being attached. That's one thing that's being attached. And then the ether is also being attached, and making an ether you can do really easily from an alcohol and an alkyl halide, like SN2 style. So you can actually make this bond really easy if we start with an alcohol, like a OH right there, with that alcohol, and then attach methyl, like methyl iodide or iodomethane, bromomethane, whatever. That's a way to make the ether, SN2 style. So let's do that as our last step. We'll kind of just work our way backwards from cut off the right side and eventually work our way backwards. So if we're going to do a ether synthesis, let's do that. Start from a benzene, same molecule with alcohol. So how do you do an ether synthesis? You take an alcohol, and it's a two-step process. What are the two steps? First step takes off the proton, makes an O minus, and then the second step is you attack something, methyl or something. So the good base we use an NaH, sodium hydride, super strong base, and then what's that with a leaving group on it? Maybe iodomethane, ICH3, and that makes the methyl ether. All right, we're not done. We still got a lot to do. Now we can maybe attach to this thing. We'll do that backwards. So how do we do that backwards? analyze the position of the squiggly line next to, to where the OH is, and we can do this with a Grignard really easily. So like that might be the Grignard, that might be the Grignard, right? Those two rings with the Grignard, and then the electrophile looks like 3 carbons, and what is squiggly next to the OH? It's next door carbon, so aldehyde, formaldehyde, ketone, or what's the fourth one? Epoxide. This would look like an epoxide connection. So all we got to do now is a 1,2 from the Grignard. MGBR. Okay, there's a Grignard. And how many carbons are we attacking? 3. 1, 2, 3. We decided on what electrophilic functional group? Epoxide of 3 carbons. H2O. So now that Grignard would attack that carbon, open up, and give you that alcohol. Alright, so we're still not done. How do you make a Grignard? From the bromide. And what reagent? Magnesium. Still not done because we had a long way to go. It's not actually, all the hard stuff's done, but we got to maneuver our way back. Ketone to a bromide cannot be done directly, but we can make a bromide. How? How is the best way to make a bromide from an alcohol? You could maybe do it from an alkene, but there's no way to easily go from a ketone to an alkene. So probably the best way is from an alcohol, because a ketone can be converted to an alcohol really easily, and an alcohol can be converted to a bromide really easily. How do you go from an alcohol to a bromide? Your best way to do it, from chapter 9, is what? It's something Br3. Something Br3. It's PBr3. PBr3. And then the ketone to an alcohol, this is cool because I was talking in the last problem about how we can go from an alcohol to a ketone to PCC. But how do we go from a ketone back to an alcohol? Well, I showed that right here. It's NABH4. NABH4 and like ethanol is the way to go from a ketone to an alcohol. So now how do we do that in this problem? Finish it off. Ketone to alcohol, NABH4. Alcohol. Cool. There we go. And essentially it's nucleophilic hydride. It's essentially H minus, attacks the ketone, opens it, or breaks it open, and then you get a alcohol. There's our synthesis. Pretty challenging one, but demonstrates a lot of reactions.